All right. Maybe.
Maybe not. Oh well. Okay.
So electromagnetic radiation travels in little packets we call photons. Last night I had out the photon cannon that actually gathered light from the moon. Okay, concentrated to a spot, looked at the eyepiece. They travel in photons, and they also travel, though, got this wave thing going on. And waves are described by having a wavelength from peak to peak or crest to crest. And the symbol for wavelength is this Greek letter. So what did somebody say? It looks like the letter A.
It was just the letter A with like a little hat.
Yeah, that's wavelength. What's C?
Oh,
E is equal to mc squared, so it's the same thing there.
yes.
It's the speed of light.
Yes.
Yep, C is the speed of light. And as it turns out, light is just one cousin of one of 7 cousins. So all of those forms of radiation travel at the same speed in a vacuum. And F is frequency. And I don't think I talked much about frequency. But frequency, so say I'm standing here. Frequency is a counter. I don't know if you've ever seen somebody like counting people. They'll have like a little clicker, and they'll click it for every time they see a person. When we do a meteor shower, sometimes I have friends that will have a clicker, and they'll count the meteors. But you have a person standing still, and you have this wave that's passing this person. And so basically this person says crest, 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 and they're counting it. This is the counter. So basically they count the number of crests that go in 1 second. So it's crests or cycles per 1 second. Okay? So units of frequency are per second. So C is equal to, what did it say? Wavelength times frequency. And C is a constant. Hey guys, there's cookies back there. Oh goodness. So C, the speed of light for all those forms of electromagnetic radiation are equal to the wavelength of that particular radiation times its frequency. So let's double check what we know. Wavelength. What has the shortest wavelength? Gamma rays or radio waves? Which is shortest?
Gamma.
Yeah, way much shorter. Very good. So here's the deal. If they have short wavelengths, I'm going to be my camera here. If they're nice and tiny short, does this make sense that they basically, if I'm counting per second, I'm going to get a lot. So they have short wavelengths, but frequencies, the cycles per second is way high. Okay, and that's kind of the way that has to mathematically work. C is a constant, okay, well, it's the speed of light. So if you told me for gamma rays, the wavelength is small, then this frequency must be large. Okay, and that's the way it is for gamma. Let's switch gears here. So what's the wavelength like for radio waves? Is it long or short? Cookie?
Oh no, thank you.
Okay. Is it long or short for radio waves, the wavelength?
Wavelength is...
It's long.
It's long. Yep, it's way long. So if it's way long, if I'm counting cycles, am I going to have a lot of cycles in 1 second or not very many cycles in 1
It's
second?
kind of low.
It's going to be very low. So here, with regard to radio, you told me that wavelength is long, and you're right, and the frequency is small. So we kind of have these two extremes. And this is like mathematically, they have what we call an inverse relationship. As one goes up, the other has to go down. It happens all the time in science. As one goes down, the other one has to go up. Because it's always going to be equal to a constant. So I've got an example here. This one, by the way, let's see, we aren't doing much with metric prefixes in here, but the metric prefix giga, capital G, means 1 billion. So here, I know it's crazy. So here we have a person counting cycles, and they're counting 30 billion cycles per second, 1001. 30 billion. Happens all the time. So that's how small and how fast these things are moving. But here's the deal. 1 centimeter, oh, you're talking about like that. What if we go ahead and cut it instead of 1 centimeter, we have a 0.5 centimeter? What happened to the frequency?
Doubles.
Yeah, yeah, exactly. The wavelength halved and the frequency doubled. That's exactly how you see it here. one more sort of scenario. These must be more energetic as we go, right? If we compare if this is A, B, and C, if we compare B to C, we're again having it, so we must be doubling the frequency. So if you half the wavelength, you double the frequency. So that's kind of how that works. Okay, so very good. I like this, let's see if you guys like this too. So up at the top we have do we have 7 cousins? 1, 2, 3, 4, 5, 6. We're missing something, aren't we?
It says microwave.
There, thank you. It's 7, yeah. So there's the 7 cousins. And exactly like you guys have been telling me, these gamma rays are really short wavelengths, radio waves are very long. We talked a little bit about scientific notation. What does it mean when I say 10 to the negative 12? Is that a big number or a small number?
Very small.
Very small. That's like 0.0000001. Okay, meters. Okay, 10 to the second, how big is that? 10 to the second?
It's 100.
100, yeah, 10 to the second's 100. So you're talking about 100 meters or so. 100 meters would be like 50 miles for one repeating unit of these energies out here. So down here we've got then what sort of object would be that size? Well, a football field or longer than a football field. Okay. A baseball here, but for visible light, check this out. The wavelength's about the size of a bacterium. Between X-rays and ultraviolet, protein, hydrogen atom. Okay. So hydrogen atom is pretty darn small, and I'm trying to think, I guess a piece of a hydrogen atom, like an electron or something, might be the gamma rays. So what are we seeing? Does this make sense? Phones down, guys. Thank you. So does this make sense? Is this what we talked about? Notice that over here we have very short wavelengths, and what's the frequency?
Very high.
Very high. 10 to the 20th, a very big number. Over here we have relatively long wavelengths, and here, I know this says 10 to the 6th, that's still a big number, but 10 to the 6th is much smaller than 10 to the 20th. 10 to the 6th, what is 10 to the 6th?
A million or 10 million?
I'm liking a million, I think. Yeah. So, a million. For those less energetic radio waves, if you count 1001, like 1 second, you got a million cycles passing a point. Okay. If you count a second here, you've got 10 to the 20th cycles passing you. That's what we're talking about, frequencies. There's energy. Now, I like these last 2 rows too. So this is where in the heck would you see these sources on Earth? Of course, radio waves be from a radio transmitter, microwaves, right? Here, this is talking about more kind of in that region. Why does it say people for infrared?
I guess because we're giving off, slower.
Exactly. It kind of goes back to this, If we take our temperature, we are oozing energy. If you watch the movie, some of the movies have aliens like the Predator, I want to say, that actually his eyes did not see visible light. His eyes actually would look for thermal signatures. And so then they kind of see these images, the IR, the infrared radiation they're oozing. Light bulb gives us visible light, X-rays. But now this one's even cooler. So this is why do we care about this in astronomy? Well, this is why we care about this in astronomy. So when it comes to collectively called celestial objects, when it comes to stuff in space, like I said, we're kind of tethered to the Earth, although we're getting better. Okay, so we need to use all of the pieces we can. There are galaxies out there. This is radio galaxy. There are galaxies out there that are invisible unless you look at those long wavelengths. Okay, we have telescopes that, what's that?
I said that's crazy.
That is crazy. We have telescopes that when there's no eyepiece to look through, you actually have to take the information and it will be in a wavelength that our eyes are not sensitive to, and then they make an image out of it. We're going to talk about our universe actually has this kind of faint signature. Like if this is our planet orbiting our sun, and of course our sun, our star, is part of the Milky Way galaxy. and then we have other galaxies. But and actually, if we use our telescope, we can only see out to a certain place. Okay, and but so as we look out to a certain edge, we see kind of the hiss of the beginning of our universe. So in the universe are all the galaxies, and the galaxies have the stars. So anyway, we're going to use that in microwave region. Next, thermal imagery, right here. Our sun, visible light, black holes. Who doesn't like black holes? So the thing about black holes, and if you're like, well, I thought black holes like sucked everything, and they aren't cosmic vacuum cleaners, but I've heard that term on documentaries. So black holes don't go around sucking everything, but they're pretty good at even if light is close enough, the light will fall into it. So they do suck light. Yeah, if it's too close, they don't go looking for it. But here's the deal: black holes. If they're present, they actually have this kind of commotion going on outside of what we call the event horizon. A commotion going on outside of the edge. They cause the commotion. And in the commotion, they create these high energy signatures that we can look for. Gamma ray bursts are associated with, is that an exploding star or colliding neutron stars, or maybe both? Okay, very high energy. So that's why we care. So here's another thing about radiation. So if you kind of picture yourself taking a piece of wood, a stick, and you're going camping, or you're camping and you have a campfire, when you put that stick into the fire, before you put that stick into the fire, it's not glowing, it's just brown, okay? So what happens once it's in the fire for a while and you take it out?
On fire.
It's on fire. And it's smoking. Have you ever seen it where
It
the
has
fire?
this little orange, like.
It kind of has the glow of an orange. I'm not talking about the fire necessarily. There is smoke, but it's the orange glow that I'm talking about. And so basically, what happened to that stick was you poked it in the fire. Here's my flame, okay? And it picked up energy from the flame, and when you took it out, it was glowing that energy. It's like, oh, I got that, right? Well, there's characteristics to that glow for us to unpack and understand, okay? And that's called, this is my glowing stick now. This is called a black body that's radiating energy. Now, if it went back to kind of just being kind of smoldering, do you think I could take this? Where'd my thing go? I just left my thing. If this was smoldering, okay, no longer glowing, if I were to get a fix on its infrared radiation, what do you think? It would still be high in the infrared region, even though it's not glowing visible light. Okay, that's just kind of how these things go. So think of that, how this all works then. So when we talk about an object, I don't know why they call it a black body, but an object that's going to glow, we look at two characteristics. We look at the color, and we look at the intensity. Now I'm going with orange. Okay, I'm going with orange. But I'm going to show you something here. I don't know if you've ever done this. I really haven't, but I can kind of picture it. If you've ever heard somebody say it's glowing white hot, okay, the color that something glows is also an indication of the temperature it's at. And we use that technique on stars all the time. Have you noticed that stars have different colors? What colors of stars are you using?
Well, we had I guess the bluish one last night.
We had Vega. Yeah, we had Vega in the telescope. Beautiful blue.
How did I miss this? I'm sorry.
It was fun. Have you ever seen red stars? Kind of reddish looking stars? The party star kind of,
I was going to say,
Arcturus is kind of a party star and it's red. Yeah, so there's reddish looking stars, bluish looking stars, whitish looking stars. I don't think I've ever really seen a greenish looking star. Orangish? What's that?
A green one?
I don't think I have.
I was gonna say.
I think what I've read is our eyes are not very sensitive to that wavelength, green. But here we have, this is the same. Can you see the transition here, guys? Okay, so what color would you call this first one on the left?
Red.
I would too. I'll put a red I'll put an R. What about the one in the middle?
Orange.
I'm liking that too. What about the last one?
Yellow.
Red, orange, yellow. Very good. So up here on the board, I'm going to go ahead and dissect visible light. Didn't I do this mnemonic device for you guys before? I'm not going to do the whole set of cousins. Here on the left, I'm going to go ahead and hit gamma. And here on the right, I'll put radio. And here in the middle, I'll put visible. And with regard to visible, it breaks out like this. Did I tell you this before? Roy, like the first name Roy, I'm writing it backwards. Roy G, like his middle initial is G, and B-I-V, like his last name is Biv. And I know you're having to kind of read backwards, Roy G. Biv. So do you guys see the Roy here?
Yes.
Okay, so red, with regard to energy, is that the most energetic or the least energetic of Roy?
The least.
The least, exactly. So this color is lowest energy, and the yellow is highest energy. And honestly, that's kind of how this whole thing works. The highest energy is actually associated with the hottest object that's glowing, and the lowest energy is associated with the coolest object. So, Vega, blue, check this out. What do you think? Compare Vega with Arcturus, red. Which one's hotter?
Oh, Vega.
Vega. Okay, and there's a little more to it than that, but there is definitely, that's kind of how it goes. So that's part of what we call Wien's law. Okay. The dominant color or wavelength emitted, so that's the color we see it, is the indication of the temperature.
So since ours is like an orange and yellow color, does that mean it's kind of hot but not as hot as some other
The
ones?
sun? And that's where I think if we were to be able to, and we're going to see a fingerprint of our sun's energy, I think it's more like a green color, but we don't see it green.
Wow.
But it is definitely kind of a coolish. Our sun is like it's like right in the middle. It's kind of a very typical star.
Wait, so since you've never said you've seen a green sun, where if you look at the sun, you probably see one because you said it was kind of green.
Well, I don't see green when I look at the sun. I don't see green star. Oh, I know. Yeah. I think I get you.
What is
If
this
you were somewhere else and you were looking at it and it was green.
Yeah, but you'd have to. It's a handicap of our eyes. I think.
Yeah.
I think. Man,
What does the star like actually look like?
what does a star actually look
I
like?
guess it just like the planet is just a big
Our star. If you've seen cool pictures of our sun, that's what a star looks like.
big ball.
A big
It
ball.
kind of looks like a
So
big
where did
ball.
the star? Housekeeping.
Where did the star come
How
from?
is a shape
That.
thing, the star?
Oh, I don't know. I think the spiky parts. I think it's because, well, in the telescope, we looked at a star, and it was, when it's not in focus, it kind of has these spikes. I don't know. So here we go, fingerprints. You asked about our star. See that 6,000 K? Of course, K, what does K stand for?
Kelvin.
Oh, Kelvin, yeah. So that's 6,000 Kelvin. That's us. That's our fingerprint. So the way you read this, the black line, the black solid line is showing you how, this is intensity along the y-axis. This is wavelength along the x-axis. That's telling us, like here in the gamma rays, it doesn't have much at all. And it doesn't have a whole lot here in the microwaves and radio waves, but it peaks actually here in the visible region. Those are all cousins. Do you see the cousins down there from short to long? So that's the fingerprint of the surface temperature of our sun. I'll ask you, you think it's hotter in the center of our sun? It's a lot hotter, but that's the surface. So what else do we have? Well, we have a star that surface temperature is 12,000 Kelvin, so twice the temperature of ours. And what can you notice about the hotter star? What can you notice about where it peaks? What color does it peak in?
It peaks in the X-rays.
Yeah.
Right here,
Yeah, it peaks in the X-rays over even shorter than visible light. Yeah. What else can you tell about it? What about its intensity?
Much more.
It's
intense.
much more.
So
Yes.
It's much hot.
Yes.
Yes.
Those are the two things that we see in stars. We can see that their intensities are higher. Okay, on these curves are called black body radiation curves. It's just like a fingerprint of how the intensity of the star is over those different types of energies. Cool. Well, what about the 3000 Kelvin star?
It peaks in the infrared.
Yeah, it pinks in the infrared. I'm liking that. So visible would be red, reddish. And then what about its intensity?
Wait.
Squatty. Yeah. Yep. That's it. That's totally it. So collectively, those are called, is it Wien's law or Stefan Boltzmann's law? I get those mixed up. But these are curves of 3 different stars. So this is a good thing that we can actually kind of take a fingerprint of a star and understand something about the star. Here's a similar figures I just showed you. Which one's our sun?
The 6,000.
The 6,000 Kelvin. Very good. So Wien's law, let's see if we can get this right. Wien's law, the hotter the object, the shorter the length of the dominant wavelength. What does dominant wavelength mean to us as we're looking at it? Dominant wavelength. Think of those,
See it?
where the peak is. Yeah, dominant just means where the peak is. You saw in that graph, that's what you'll see it as. You got it, that's Wien's law. Stefan Boltzmann's law is the other thing you guys told me, that the hotter it is, the more intense, the whole graph goes up and goes to the shorter wavelengths, goes to the left. An object gets hotter, as an object gets hotter, the intensity with which it emits electromagnetic radiation increases. So those are actually Wien's law and Stefan Boltzmann's law, and it's kind of intuitive. It sounds like you guys got it. So again, why do we care? It's because we're kind of tethered to, for now, this Earth, and we got to use all the information we can to understand other stars. As we understand our star more, we understand other stars more, and we understand other stars more, we understand our own sun more. Let's see, we didn't talk about temperatures yet? You guys got cake for Kelvin. I thought we did. Did we do this yet?
Yeah, I think we did a little bit.
Okay.
A little bit.
So when you guys go out, when you guys check the weather in the morning, what temperature scale do you look at?
Fahrenheit.
Fahrenheit, yeah, exactly. And that's old-timey English. We all do it, okay? Metric would be Celsius. And with regard to water freezes at 32 Fahrenheit, 0 Celsius. Water boils at 212 Fahrenheit, 100 Celsius. So you guys told me that K after 6,000 K, that stands for Kelvin. And that's also metric. So we have Celsius is metric and Kelvin is metric. And they shake hands quite nicely. They are offset by 273.15 units. A unit Celsius is the same as a unit Kelvin, so that's nice. They're just offset. So the thing about the Kelvin scale, what's absolute zero?
0.
0. Anything else you know about absolute zero?
Frozen in place. Nothing
Frozen in
moves.
place. Yeah. This is my matter, and so all matter has motion, whether it's just like this is matter, of course, it's made up of atoms and kind of joined together and all that. So it has motion, it's probably just vibrational. There's rotational, and there's translational. But at absolute zero, all matter stops moving. So that's a very cool place. Okay. All right. So this actually is something that Sir Isaac Newton found, that he could take. Now I'm not sure how a prism does what it does, but the way it's cut, it's just a slab of glass, and the way it's cut is that it takes light coming in. This would be sunlight, and it can break it into. What happens is the light, which is all of these colors, right? It's all squished together. That's white light. So what a prism does is break it out into its different wavelengths. The way it does this is because red is bent the least and violet is bent the most. Can you see that on that? Red is bent the least and violet is bent the most. That bending is called refraction, by the way. But my point here is that you can take white light and break it out into its colors. All right. So this actually is the signature of our sun. When I see something like this, I always think of like the DNA. You know how they kind of look like
Oh, and it has a little black line.
Yeah, the little black lines, exactly. And where the little black lines are an indication of your genetic markers, okay, DNA. So this is a picture of what, I think it's Fraunhofer, found when he used a magnifying glass to look at rainbow or spectrum from our sun. And when he used a magnifying glass, he could see these lines, okay? And he's like, what? And he's like, there must be something probably wrong with my prism or my magnifying glass. And so he did it again, like what we do in science. Can you repeat it? And he saw these lines. And as it turns out, these lines are an indication of, from the sun, is sending us a signature of what sort of elements are on the sun. So when I say elements, I'm looking like this, right? Elements, like from the periodic table, okay? So the thing is that, well, I'm going to talk more about that. So these, if you know what you're looking at, and I kind of tease chemists because it's like, you just pull up a library and you can map that. It's like a DNA signature. What do? Well, you just pull up the little software that will help analyze that for you. So here we go. No, do you guys see any lines there? Okay, no lines. So there must be, that's a pure light coming with no interference. It's called a continuous spectrum. Anybody know sodium? What is the letters for sodium?
Na.
Na, very good. Sodium, perfect. So, and I'm gonna try to convince you what's making these lines here, but can you see sodium? Kind of in this bluish region, it has these deep, deep, okay, and then over in the yellow region, deep, deep, these deep, 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 okay? So those like 7 lines, if you know what you're looking for, are an indication of the presence of sodium. Hydrogen, calcium, mercury. What's the symbol for hydrogen?
H.
Perfect. What's the symbol for calcium?
Ca.
Tough one. Mercury.
And
It's
it's
H. What's the other letter though?
you said it's H.
It starts with H. H.
It's not He because that's helium, right?
Not He.
So
HN.
Not H.
I don't know.
It's H.
HU.
No.
HC.
Nope.
You got a 1 in 24 chance.
HG. Yes, right.
H.
I'm looking at. I'm tripping.
Don't ever guess that.
HG. HG.
Yeah, because gold is AU. So
Yeah, gold is
Say
AU.
yeah.
Yep, and silver is
Right.
AG. You got it. So how do these lines come? And I'm going to actually mark something on these lines. These are called bright line spectra. Bright line spectra. Bright line spectra. So how do they come? This is how they come. This is an atom. Okay, so if this atom has only 1 proton, did we talk about this? What element is it?
hydrogen.
It is hydrogen. I get my classes mixed up, but it is hydrogen. 1 proton, it is hydrogen. So if it's neutral, then it's going to have 1 electron. Is there a lot of hydrogen in this universe?
Yes.
Yes. Yeah, if we were to kind of step back from our planet, from our solar system, from our galaxy, look at all of the galaxies in the universe, you'd be looking at hydrogen's like 99 point whatever % of all the atoms. So that's kind of the structure. What about 2 protons? What element is that? It is helium. Oh, this is helium. And also you can look at the periodic table. So 1 is hydrogen, 1 proton, 2 protons is helium. And if it's neutral, it has 2 electrons. Now this looks a little funky. It doesn't look like the atoms we've been talking about. To look at this, see where it kind of looks like a bullseye? In the center there, that's where you're going to put your protons, okay? In the center there. Now, those lines are actually showing you where the electrons can be, and they're also showing you how much energy the electrons can have. So it's possibilities. We're picking on hydrogen. So if the middle of my hands is the center of an atom, And this ring right here is where an electron is. So how many electrons does a hydrogen atom have?
Oh, 2. Wait, no, 1.
One. Yeah, one electron. Yep. So this would be what we call its ground state, its lowest energy. But do you see these circles? It can actually skip up here. Do you think if it skips up from this energy state to this energy state, do you think it needs energy or it releases energy? So if it goes from here to here, it needs energy, exactly. It sucks energy. Okay. Now, here though, we see it going from a high energy to a low energy. Do you think it sucks energy or releases energy? It releases, yep. So this one releases, and this one sucks energy. Okay? Very good. So here's the deal. Atoms of different elements are unique in the number of protons they have in their nucleus. Okay, that's the number on the periodic table. They are also then unique with regard to the electrons they have. Okay, and the electrons can do these funky things. They can do these different jumps specific for the element. And that's where you get kind of the fingerprinting part. All right, so here we go. We have a bunch of, well, we have a bunch of. See how this set is falling down and the other set is going up. So the ones falling down, do you think they're releasing energy or sucking energy? These guys. They're falling down. They're going from a high to a low. They're releasing energy. Yep. And actually, do you see where you have the word emission here? Those are emission lines. Both of those are. These guys right here, what does absorption mean? Like if you take a paper towel and you're trying to get some
Soaks it up.
soaks it up, exactly. So these guys are soaking up energy. So here's the deal. These guys down here, emission, will be bright. These emission ones will be bright. These absorptions one will be dark. Dark lines, bright lines. Exactly. If you kind of picture what's going on, it's not bad. Well, enough of all this. I have some examples to try to show you this here in a minute. But, so how does this work here on Earth? How can we actually get any information from outer space? And this slide's going to kind of show you. So here's the deal. This isn't actually what I was going to. We can, if there's nothing to mess up our spectrum, our information. Notice here we get no lines. Does that make sense? There's nothing to mess it up. Here we have a cloud of gas to mess it up. We have a cloud of gas to basically interrupt that energy we're getting from that source. Does it look like it was absorbing? Are those lines absorbing, or are those lines created by emitting energy? How many people think it looks like it's absorbing energy to make those lines? Me too. I agree. It's absorbing energy to make those lines. Perfect.
So, question.
Mm-hmm.
Since those lines are created by the absorption of energy through a cloud of gas,
Mm-hmm.
are you saying like when the sun shoots a beam of light and then we receive it and it has those gaps in it, we figure out which element created those gaps?
Yes. Yes. And exactly. And I think this is exactly what you're saying. This cloud of gas is like, for the few slides ago when we saw the sun with the dark lines, that gas, those dark lines were created by the sun's atmosphere. Not the Earth's atmosphere, but the sun's atmosphere. The gases associated with the sun.
When it shot the pure light, I guess, through the atmosphere, the ones that were missing the atoms that it needed, it absorbed it as it was shooting it like toward Earth.
What happened was, this is how I picture it. So I think you're onto it. So this is the sun, and I know it's weird to think of, but the sun has kind of an atmosphere, and like you said, it's shooting light at us. So here's the deal. As it came out of the sun, it was continuous. I'll put CONT for continuous. As it interacts with atoms in the atmosphere, those atoms are sucking, we have these, those atoms are sucking energy to create those dark lines. So when we see it over here, we see it with absorption lines. Did you catch that, Reed? I think I lost him. But anyway, yes. All right, so that is what we call the dark line spectrum or the absorption line spectrum. Check this out now. Here's one for you. What if you aren't looking at the continuous source and the sucking of energy, but instead you're over here and you're kind of looking at the glow of the cloud. You're kind of looking at the glow of the cloud, okay? So in this case, does it look like, how many people thinks it looks like it's sucking energy? How many people think it looks like giving up energy? It is giving up energy. This is called a bright line spectrum or emission spectrum. Bright line and emission mean the same thing. All right. So I have one last topic, and then I have our little demo thing up here I want you to see. The last thing I want to talk about, actually, it's going to come up with stars too. And the best way I know to do is to do it with sound. So the way this works is, now I was going to use my chair, but I don't think so. If you are standing still and you have something that's emitting sound, okay, maybe you're at a racetrack and you see it and you're kind of like in the middle of the long stretch, you kind of hear it kind of go like that, okay? So the deal is when something is moving towards you, the sound will ramp, the pitch will ramp up. A ramping up pitch means a shortening of wavelengths. After it passes you, the pitch will go down, the lengthening of wavelengths of sound. So it goes like that. Okay, so it goes, I know, right? So it gets shorter and then it gets longer. So literally, if you can think of kind of that thing that's emitting the sound is those wavelengths are getting squished as it's coming towards you. Okay? Something getting shorter wavelength in terms of red or blue, something getting shorter wavelength is blue compared to red anyway. So we call that the blue shift. So blue shift, it's red shift. Okay? And we see this with stars. So here we go. Here's our source train. We have two observers. If the train's standing still, there's no shift. Here the train is moving from left to right, and the dude on the right, actually, what color shift does he got?
We got that blue.
He's got the blue shift, so he would hear the pitch go up or down. What do you think? How many people think it would go up? How many people think it would go down? It go up. Pitch will go up. Pitch will go up, and here pitch will go down. All right, so forget a moving train. Now our source is a moving light. Okay, so we have the light moving towards the right again, and this guy will actually see the color of light shift to the blue region, and this guy will see it shift to the red region. Okay. All right. Okay, so before you go, you gotta check this out. So come on up here, guys. So you need to pass this around. Take one of these that has an arrow in it.
Arrow.
An arrow. You'll know what I mean. So get one of those little squares that has an arrow. Now those little squares are called diffraction gratings. They're basically pieces of plastic that have lines in them. And the things I'm going to turn on, so you need one that has the arrow, and you're going to put the arrow up. So I have,
but I'm saying, does the word face you, or does it matter?
there should be an arrow. It doesn't matter.
Okay.
Yeah. Okay, so here we have different, I think this is neon, and I think this is hydrogen. I'm doing one at a time. Okay, you might have to get kind of close. You have to get a little closer, guys, but not too close. So like about this far, and you have to kind of look to the side of your square.
You see the rainbow?
You see the lines? You should see some lines. Do they look like emission or absorption lines? You might have to kind of look in the side. Yeah, you can come over here.
Oh no, it looks the same. Oh, I see you.
Where's the bag, though, guys?
I I see blue and red.
You guys see some lines?
Yeah, you got really look in here, like.
Yeah, I see it now.
And close on your eye, yeah,
Yeah,
yeah.
I see it now.
So you try to forget that.
Yeah, I see it now.
Over here.
They're like on the side.
Yeah,
Oh, yeah.
On the side, yeah.
I'll figure it out.
Yeah,
Yeah.
Courtney, I think you're too close, son. Hey, Courtney, you have to hold it close, far away.
Okay.
See it. It was just
Oh, you
kind of-
can see it?
I can see it. I can see it from about right here.
Did everybody see it?
Yeah,
They're blue and red.
yeah.
And there's kind of a yellowish and red in the middle.
Did you
Yeah, right
see it,
here,
Aaron?
yeah, right there.
Okay, so that was hydrogen, and what's the symbol for neon? What's the letters? N-E.
Oh, no. Oh, I see.
I got a whole lot of red.
I see red, green, and yellow though.
You see
But
the
it's a
set
bunch
of
of
lines?
red.
It
Huh?
is
You see a set of lines?
Oh, yeah.
Yeah.
Red,
There's like a
green,
bunch of
yellow,
red, a
and
bunch of orange, a bunch of yellow,
And
a
blue.
bunch of
It's
green.
really, really light.
There's like one blue.
That's fine.
So those are fingerprints. When you're done, go ahead and leave the little square thingy there, and we'll see you. Have a great, we don't have class Friday.
Sure that we can.
See you on Monday. And you see the test is bumped for Wednesday. Everybody see the test is bumped.
Yeah.
I don't got no, I ain't got the paper, Miss Snipes.
Right, it's like an insert.
Jeremy,
I don't know.
Whoever showed up.
Smoking the back.
Smoke a little more.
So because you smoke around, I got secondhand smoke.
Don't forget to get those labs in.
Yes.
I don't like those. Get smoke on the roof.
Can I get the, lab?
Binoculars?
Yeah,
Is that what you meant?
yes.
Hey, Allie, put held hands and, I know what I have to tell them.
This stuff's fine. I'll
Angela
play that
wanted to
later.
see you real quick. She wants to see you again.
This week.
Yeah. Let's see.
I'm not going to that river.
English coffee. High B, yay, high B. Still smells like burnt popcorn. Man, that's not good.
Oh, man. Remember when she burnt that popcorn? Yeah. It still smell like that. That was so long ago, wasn't it?
It was. It was.
Oh.
I'm gonna print one out right quick. Is that for me?
This is time management stuff.
Okay.
I'll submit the essay in a couple hours.
Okay.
I just need to get on the computer.
Very good. Thanks, Aaron. All right.